implicit differentiation, tangents and normals, and logarithmic differentiation. Welcome friends. In the previous sessions of this MOOC course on differential calculus, we have been concerned with differentiating functions that are given by equations of the form y equal to f of x. In this session, we consider methods for differentiating functions for which it is difficult or impossible to express them in the form y equal to f of x. We also describe the method of differentiating functions of the form y equal to u power v, where both u and v are functions of x. In this case, it is useful to take logarithms on both sides and then differentiate. This process, known as logarithmic differentiation, is also useful when y is a product of several terms. An equation of the form y equal to f of x is said to define y explicitly as a function of x because the variable y appears alone on one side of the equation. However, sometimes functions that are defined by equations in which y is not alone on one side. For example, the equation yx minus y plus 7 equal to 3x is not of the form y equal to f of x. However, this equation still defines y as a function of x, since it can be written as y into x minus 1 equal to 3x minus 7, which gives y equal to 3x minus 7 divided by x minus 1, where x not equal to 1, in which y is explicitly defined as a function of x. Thus, we say that yx minus y plus 7 equal to 3x defines y implicitly as a function of x, the function being f of x is equal to 3x minus 7 divided by x minus 1, where x not equal to 1. As another example, consider the unit circle centered at the origin given by the equation x square plus y square equal to 1. If we solve this for y in terms of x, we obtain y equal to plus square root of 1 minus x square or y equal to minus square root of 1 minus x square. Now, y equal to plus square root of 1 minus x square is a function with natural domain the closed interval minus 1 1, and its graph is the upper semicircle of the circle x square plus y square equal to 1. Similarly, y equal to minus square root of 1 minus x square is also a function with the same natural domain, the closed interval minus 1 1, but having lower semicircle of the circle x square plus y square equal to 1 as the graph. We conclude that there are two functions that are defined implicitly by x square plus y square equal to 1, namely f of x is equal to square root of 1 minus x square and g of x is equal to minus square root of 1 minus x square. It is to be noted that the complete circle x square plus y square equal to 1 does not pass the vertical line test and hence is not itself the graph of a function of x. However, the upper and lower semicircles do pass the vertical line test and hence are graphs of functions. In general, if we have an equation in x and y, then any portion of its graph that passes the vertical line test can be viewed as the graph of a function defined by the equation. Thus, we make the following definition. We will say that a given equation in x and y defines the function f implicitly if the graph of y equal to f of x coincides with a portion of the graph of the equation. As an example, we see that the graph of the parabola y square equal to 4x is not the graph of a function of x, since some vertical lines touch the curve at more than one point. For example, in the figure, the vertical line x is equal to 5 touches the curve at 2 points. However, if we solve this equation for y in terms of x, we obtain two equations, y equal to 2 square root of x and y is equal to minus 2 square root of x, whose graphs pass the vertical line test and are portions of the graph of y square equal to 4x. Thus, the equation y square equal to 4x implicitly defines the functions f of x is equal to 2 square root of x and g of x is equal to minus 2 square root of x. In the above examples, Simple algebraic operations was enough to obtain explicit functions associated with the given equation in x and y that defines the functions implicitly. But this is not always possible in general. For example, the equation x cube plus y cube equal to 9xy can be solved for y in terms of x, but the resulting formulas are too complicated. Moreover, it is not the graph of any one function of x, as the vertical line test fails here. Now we show that the equation x cube plus y cube equal to 9xy defines at least 3 functions implicitly. The following 3 curves are graphs of the functions as they pass the vertical line test. Moreover, each of them coincide with a portion of the graph of the equation x cube plus y cube equal to 9xy, and the union is the graph of the equation x cube plus y cube equal to 9xy. Hence, the equation x cube plus y cube equal to 9xy defines at least 3 functions implicitly. The curve given by x cube plus y cube equal to 9xy, called a folium, dates back to French mathematician René Descartes in 1638. The Latin word folium means leaf. As observed above, the curve x cube plus y cube equal to 9xy can be divided into separate arcs that are the graphs of functions of x. The curve was first proposed by the French mathematician and philosopher René Descartes in 1638. Descartes challenged the French mathematician Pierre de Fermat to find the tangent line to the curve at an arbitrary point, since Fermat had recently discovered a method for finding tangent lines. Fermat solved the problem easily, something Descartes was unable to do. Now, the slope of the tangent line can be found easily using implicit differentiation. The graph of the equation x cube plus y cube equal to 9xy has a well-defined slope at nearly every point, because as observed above, it is the union of the graphs of functions y equal to f1 of x, y is equal to f2 of x, and y equal to f3 of x, which are differentiable except at the origin and at the point where the tangent is perpendicular to the x-axis. But how do we find the slope when we cannot easily solve the equation to find the functions? The answer is to treat y as a differentiable function of x and differentiate both sides of the equation with respect to x using the differentiation rules for powers, sums, products, etc. and the chain rule. Then solve for dy by dx in terms of x and y together to obtain a formula that calculates the slope at any point ordered pair xy on the graph from the values of x and y. This process of finding dy by dx is called implicit differentiation. We note that there are certain equations such as y equal to cos of xy that cannot be solved for y by any elementary method. Finding dy by dx of such functions are also possible by implicit differentiation. We begin with a simple example. For the implicit function xy equal to 1, differentiating both sides with respect to x gives d by dx of xy equal to 0, which by an application of product rule gives x into d by dx of y plus y into d by dx of x equal to 0. That is, x into dy by dx plus y equal to 0. That is, dy by dx is equal to minus y by x. Note that this formula for dy by dx involves both x and y. In order to obtain a formula for dy by dx that involves x alone, we would have to solve the original equation xy equal to 1 for y in terms of x, which is y equal to 1 by x, and then substitute this in the above equation, obtaining dy by dx equal to minus 1 by x square. We also observe that from the equation xy equal to 1, we can immediately write y in the explicit form y equal to 1 by x, which on differentiation gives dy by dx equal to minus 1 by x square as obtained above. We use implicit differentiation to find dy by dx if 6y square plus cos y equal to x square. taking derivatives on both sides with respect to x, we obtain d by dx of 6y square plus cos y equal to d by dx of x square, implies 6 into d by dx of y square plus d by dx of cos y equal to 2x, implies 6 into 2y dy by dx plus minus sin y dy by dx equal to 2x, implies 12y dy by dx minus sin y dy by dx equal to 2x. Solving for dy by dx, we obtain dy by dx equal to 2x all divided by 12y minus sin y. Note that this formula involves both x and y. In order to obtain a formula for dy by dx that involves x alone, we would have to solve the original equation for y in terms of x and then substitute in the above equation. However, in this example, it is impossible to do this, so we are forced to leave the formula for dy by dx in terms of x and y. Now, we find the slope of the circle x square plus y square equal to 25 at any point ordered pair 4 minus 3. Differentiating the given equation with respect to x, we obtain 2x plus 2y dy by dx equal to 0, implies dy by dx equal to minus x by y. Hence, the slope at 4 minus 3 is dy by dx calculated at ordered pair 4 minus 3 equal to minus x by y calculated at the ordered pair 4 minus 3 equal to minus 4 divided by minus 3 equal to 4 by 3. We have obtained the above slope by using implicit differentiation. Now, let us examine the way of finding the slope explicitly as follows. The given equation of circle is not the graph of a single function of x. Its graph can be viewed as the combination of graphs of two differentiable functions, y1 is equal to square root of 25 minus x square and y2 is equal to minus square root of 25 minus x square. The point ordered pair 4 minus 3 lies on the graph of y2 is equal to minus square root of 25 minus x square, and hence the required slope is dy2 by dx calculated at the ordered pair 4 minus 3 equal to minus 2x divided by 2 into square root of 25 minus x square calculated at the ordered pair xy equal to the ordered pair 4 minus 3 equal to 4 by 3. We note that the derivative formula dy2 by dx equal to minus of minus x by square root of 25 minus x square can be obtained from y2 equal to minus square root of 25 minus x square by an application of power rule of differentiation, or can be obtained from dy by dx equal to minus x by y by substituting y equal to y2 equal to minus square root of 25 minus x square. Now, we find the slopes of the curve 3y square minus 2x plus 30 equal to 0 at the points ordered pair 21 2 and the ordered pair 21 minus 2. Differentiating implicitly yields d by dx of 3y square minus 2x plus 30 equal to d by dx of 0 gives 3 into d by dx of y square minus 2 into d by dx of x plus d by dx of 30 equal to d by dx of 0 gives 6y into dy by dx minus 2 equal to 0 gives dy by dx equal to 1 by 3y. At the ordered pair 21 2 we have y equal to 2, and at ordered pair 21 minus 2 we have y equal to minus 2. So, the slopes of the curve at these points are dy by dx calculated at x is equal to 21 and y equal to 2 equal to 1 by 6, and dy by dx calculated at x is equal to 21 and y equal to minus 2 equal to minus 1 by 6. Now, let us come to the problem of determining the tangent to the volume of Descartes x cube plus y cube equal to 3xy. We also find an equation for the tangent line to the volume of Descartes at the point ordered pair 3 by 2 3 by 2. We also ask at what points in the first quadrant does the tangent line to the volume of Descartes becomes horizontal. Differentiating both sides of the given equation implicitly, we obtain d by dx of x cube plus y cube equal to d by dx of 3xy gives 3x square plus 3y square dy by dx equal to 3x dy by dx plus xy gives x square plus y square dy by dx equal to x dy by dx plus y, gives dy by dx equal to y minus x square divided by y square minus x. At the point ordered by a 3 by 2 3 by 2, we have x is equal to 3 by 2 and y equal to 3 by 2. So, from the above expression for dy by dx, the slope m of the tangent line at this point is m equal to dy by dx calculated at x equal to 3 by 2 and y equal to 3 by 2 equal to 3 by 2 minus 3 by 2 square divided by 3 by 2 square minus 3 by 2 equal to minus 1. Thus, the equation of the tangent line at the point ordered by a 3 by 2 3 by 2 is y minus 3 by 2 equal to minus 1 into x minus 3 by 2 or x plus y equal to 3. We note that a tangent line is horizontal at the points where dy by dx equal to 0, and from the expression for dy by dx, this occurs only where y minus x square equal to 0 or y equal to x square. Substituting this expression for y in the equation x cube plus y cube equal to 3xy for the curve yields x cube plus x square all cube equal to 3x cube, gives x power 6 minus 2x cube equal to 0, gives x cube into x cube minus 2 equal to 0, whose solutions are x equal to 0 and x equal to 2 power 1 by 3. The solutions x equal to 0 and x equal to 2 power 1 by 3 yields the points ordered by a 0 0 and ordered by a 2 power 1 by 3 2 power 2 by 3 respectively on the folium. Of these two, only ordered by a 2 power 1 by 3 2 power 2 by 3 is in the first quadrant. Substituting x equal to 2 power 1 by 3 and y equal to 2 power 2 by 3 into the expression for dy by dx, we obtain dy by dx calculated at x equal to 2 power 1 by 3 and y equal to 2 power 2 by 3 equal to 0 divided by 2 power 4 by 3 minus 2 power 2 by 3 equal to 0 as expected. Hence, ordered by a 2 power 1 by 3 2 power 2 by 3 is the only point on the folium of Descartes in the first quadrant at which the tangent line is horizontal. We use implicit differentiation to find the second derivative d square y by dx square of 5x cube minus 7y square equal to 10. Differentiating both sides of 5x cube minus 7y square equal to 10 with respect to x yields 15x square minus 14y dy by dx equal to 0, from which we obtain dy by dx equal to 15x square divided by 14y. Differentiating both sides of the above yields with the use of quotient rule that d square y by dx square equal to 14y into 30x minus 15x square into 14 dy by dx all divided by 14y the whole power 2. Substituting dy by dx into the above equation and simplifying using the original equation, we obtain d square y by dx square equal to 14y into 30x minus 15x square into 14 into 15x square divided by 14y all divided by 196y square equal to 420x into y square minus 225x power 4 all divided by 196y cube. Alternatively, we can employ implicit differentiation to obtain the second derivative from the equation 15x square minus 14y dy by dx equal to 0. Differentiating both sides with respect to x yields by an application of product rule of differentiation and the chain rule that 15 into 2x minus 14 into dy by dx into dy by dx minus 14y into d square y by dx square equal to 0. That is 30x minus 14 into dy by dx the square minus 14y into d square y by dx square equal to 0. Substituting dy by dx equal to 15x square divided by 14y, the above equation gives 30x minus 14 into 15x square divided by 14y the whole square minus 14y d square y by dx square equal to 0. That is d square y by dx square equal to 420 x into y square minus 225 x power 4 all divided by 196 y cube on simplification. A line is normal to a curve at a point if it is perpendicular to the curve's tangent line at that point. If m1 is the slope of the tangent at that point, then minus 1 by m1 is the slope of the normal at that point. As an example, let us find the tangent and normal to the circle x square plus y square equal to 25 at the point ordered pair 4 minus 3. We have observed earlier in this session that the slope of the circle x square plus y square equal to 25 at the point ordered pair 4 minus 3 is dy by dx calculated at 4 minus 3 equal to 4 by 3. Hence, slope of the tangent is m1 equal to 4 by 3 and the slope of the normal at that point is minus 1 by m1 equal to minus 3 by 4. Hence, the tangent to the circle x square plus y square equal to 25 at the point ordered pair 4 minus 3 is the line y minus of minus 3 equal to 4 by 3 into x minus 4, that is y equal to 4 by 3 x minus 25 by 3. The normal to the circle x square plus y square equal to 25 at that point ordered pair 4 minus 3 is the line y minus of minus 3 equal to minus 3 by 4 into x minus 4, that is y equal to minus 3 by 4 x. We bring the attention of the student to note that if y equal to mx plus c is a tangent to a curve at a given point, then the line y equal to minus 1 by m into x plus c is perpendicular to the tangent line, but need not be a normal to the curve at the given point. As an illustration, in the above example, if we replace 4 by 3 with minus 3 by 4 in the equation of tangent y equal to 4 by 3 x minus 25 by 3, we obtain y equal to minus 3 by 4 into x minus 25 by 3, which by looking the figure shows that this is not a normal to the circle at the point ordered pair 4 minus 3. So, to find a normal at a point, we have to replace m by minus 1 by m in the point slope form of the equation of the tangent line. Now, let us conclude the discussion on implicit differentiation by proving the power rule for differentiation of rational powers by implicit differentiation. Power rule for rational powers. If r is a rational number, then d by dx of x power r equal to r into x power r minus 1. To prove this, we take r equal to p by q, where p and q are integers with q greater than 0. Then we take y equal to x power r equal to x power p by q equal to qth root of x power p. Then we obtain the equation y power q equal to x power p, in which y is an implicit function of x. Already we are familiar with power rule for integers. Using the same and with the help of the chain rule, differentiating the above equation with respect to x gives q into y power q minus 1 into dy by dx equal to p into x power p minus 1. If y not equal to 0, we can then divide both sides of the above equation by q into y power q minus 1 to solve for dy by dx, obtaining dy by dx equal to p into x power p minus 1 divided by q into y power q minus 1 equal to p into x power p minus 1 all divided by q into x power p by q all power q minus 1 equal to p by q into x power p minus 1 divided by x power p minus p by q equal to p by q into x power p minus 1 minus of p minus p by q equal to p by q into x power p by q minus 1 equal to r into x power r minus 1, proving the result. Logarithmic differentiation. Now, we are going to differentiate the functions of the form y equal to u power v, where both u and v are functions of x. It is found useful to take logarithms on both sides and then differentiate the same. This process known as logarithmic differentiation, also is useful when y is a product of several factors. We find dy by dx where y equal to sin x all power cos x. Given y equal to sin x all power cos x. Taking natural logarithm on both sides, we obtain log y equal to cos x into log of sin x. Now differentiating both sides of the above equation with respect to x, we obtain d by dx of log y equal to d by dx of cos x into log of sin x. Then applying the product rule of differentiation on the right hand side, we obtain d by dx of log y equal to cos x into d by dx of log of sin x plus d by dx of cos x into log of sin x equal to cos x into 1 by sin x into d by dx of sin x minus sin x into log of sin x equal to cos x into 1 by sin x into cos x minus sin x into log of sin x. That is 1 by y into dy by dx equal to cot x into cos x minus sin x into log of sin x. Thus, dy by dx equal to sin x all power cos x into cot x into cos x minus sin x into log of sin x. We find dy by dx when y equal to sin x all power x plus cos of x power tan x. Given y equal to sin x all power x plus cos of x power tan x. Here put u equal to sin x all power x, v equal to cos of x power tan x, so that y equal to u plus v. Then dy by dx equal to du by dx plus dv by dx. Now the determination of du by dx. Now log u equal to x into log of sin x. So on differentiating both sides with respect to x, we get d by dx of log u equal to d by dx of x into log of sin x, or 1 by u into du by dx equal to x into 1 by sin x into d by dx of sin x plus log of sin x into 1 equal to x into cot x plus log of sin x, so that du by dx equal to sin x all power x into cot x plus log of sin x. Now log v equal to tan x into log of cos x. So on differentiating both sides with respect to x, we get 1 by v into dv by dx equal to tan x into 1 by cos x into d by dx of cos x plus log of cos x into sec square x equal to sec square x into log of cos x minus tan square x, so that dv by dx equal to cos x all power tan x into sec square x into log of cos x minus tan square x. Substituting the equations 4 and 5 in the equation 3, we get dy by dx equal to sin x all power x into cot x plus log of sin x plus cos of x power tan x into sec square x into log of cos x minus tan square x. We find dy by dx where y equal to x power 1 by 2 into 1 minus 2x all power 2 by 3 all divided by 2 minus 3x all power 3 by 4 into 3 minus 4x all power 4 by 5. Taking logarithm on both sides, we obtain log y equal to 1 by 2 into log x plus 2 by 3 into log of 1 minus 2x minus 3 by 4 into log of 2 minus 3x minus 4 by 5 into log of 3 minus 4x. Differentiating with respect to x, we obtain 1 by y into dy by dx equal to 1 by 2 into 1 by x plus 2 by 3 into minus 2 divided by 1 minus 2x minus 3 by 4 into minus 3 divided by 2 minus 3x minus 4 by 5 into minus 4 by 3 minus 4x equal to 1 by 2x minus 4 by 3 into 1 minus 2x plus 9 divided by 4 into 2 minus 3x plus 16 divided by 5 into 3 minus 4x. Hence, dy by dx equal to y into 1 by 2x minus 4 divided by 3 into 1 minus 2x plus 9 divided by 4 into 2 minus 3x plus 16 divided by 5 into 3 minus 4x. We find dy by dx where y equal to square root of x square plus x plus 1 all divided by x square minus x plus 1. Given y equal to x square plus x plus 1 all divided by x square minus x plus 1 all power 1 by 2. Taking logarithm on both sides, we get log y equal to 1 by 2 into log of x square plus x plus 1 minus log of x square minus x plus 1. Now differentiating both sides with respect to x, we obtain 1 by y into dy by dx equal to 1 by 2 into 1 by x square plus x plus 1 into d by dx of x square plus x plus 1 minus 1 by 2 into 1 by x square minus x plus 1 into d by dx of x square minus x plus 1 equal to 1 by 2 into 1 by x square plus x plus 1 into 2x plus 1 minus 1 by 2 into 1 by x square minus x plus 1 into 2x minus 1. dy by dx equal to y into 2x plus 1 divided by 2 into x square plus x plus 1 minus 2x minus 1 divided by 2 into x square minus x plus 1, or dy by dx equal to 1 minus x square all divided by x square plus x plus 1 all power 1 by 2 into x square minus x plus 1 all power 3 by 2. If x power y into y power x equal to 1, let us find dy by dx. Taking logarithm on both sides and noting that log 1 equal to 0, we obtain y into log x plus x into log y equal to 0. Differentiating both sides with respect to x, we get y into 1 by x plus log x into dy by dx plus 1 into log y plus x into 1 by y into dy by dx equal to 0. This implies log x into x by y into dy by dx equal to minus of y by x plus log y. Hence, dy by dx equal to minus of y plus x log y all divided by x plus y log x into y by x. If y power cot x plus tan inverse x all power y equal to 1, let us find dy by dx. Let u equal to y power cot x and v equal to tan inverse x all power y. Then u plus v equal to 1. Taking logarithm on both sides for u, we obtain log u equal to cot x into log y. Differentiating both sides with respect to x, we get 1 by u into du by dx equal to cot x into 1 by y into dy by dx plus log y into minus cosec square x. Thus, du by dx equal to y into cot x into cot x divided by y into dy by dx minus cosec square x into log y. Taking logarithm on both sides for v, we obtain log v equal to y into log of tan inverse x. Differentiating both sides with respect to x, we get 1 by v into dv by dx equal to y into 1 by tan inverse x into 1 by 1 plus x square plus log of tan inverse x into dy by dx. Thus, dv by dx equal to tan inverse x all power y into y divided by 1 plus x square into tan inverse x plus log of tan inverse x into dy by dx. Now, from the equation 1, du by dx plus dv by dx equal to 0. This implies y power cot x into cot x divided by y into dy by dx minus cosec square x into log y plus tan inverse x all power y into y divided by 1 plus x square into tan inverse x plus log of tan inverse x into dy by dx equal to 0. Hence, y power cot x into cot x divided by y plus tan inverse x all power y into log of tan inverse x into dy by dx equal to y power cot x into cosec square x into log y minus tan inverse x all power y into y all divided by 1 plus x square into tan inverse x. Thus, dy by dx equal to y power cot x into cosec square x into log y minus tan inverse x all power y minus 1 into y divided by 1 plus x square all divided by y power cot x minus 1 into cot x plus tan inverse x all power y into log of tan inverse x. Conclusion. In this session, we discussed the implicit differentiation and logarithmic differentiation through various examples. The ways of finding the tangent and normal to a given curve at a given point using implicit differentiation have been illustrated through examples.